Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
Now, all stars formed in a particular sequence. They have a life cycle, meaning that they can also get to a point where they will eventually, as it were, die or change to something else. As a matter of fact, they started with a ball of gas and dust particles called nebula in space, something like this. Can you see the diagram below? What we call stellar nebula. Are you listening to me?
Yeah.
Now, this nebula could be as a result of a previous star that already outlived its lifespan, exploded, and poured gas particles into space, which started all over again to form another star. And all of these processes, according to the theory, the processes take a long period of billions of years. So it could have been a previous star, like I said, that outlived its lifespan, exploded, poured into space gas particles that started all over again, gathering together. In fact, our sun, are you listening? Our sun
Yes, awesome.
is a product of a previous star. Do you understand?
Okay.
Our sun is a product of a previous star, just like several stars are product of previous stars that have lived their lifespan, exploded in a process.
So, what's the difference between a nebula and a supernova?
Okay, a supernova is the explosion that occurs.
What's a nebula?
A nebula is the gas particles that form, usually mostly hydrogen gas and other dust particles that are poured into space. Pardon?
How come they are colored? Like they have different colors?
Color? No, that's just to tell you that it's an explosion. Initially the star was hot, so during the nebula, the supernova, it just exploded and poured the gas particles into space. It's just an illustration to show you that it's like something that was burning and then it exploded and poured stuff into space. By the way, it's not all stars that go through that process. A star that can get to the point of supernova will be bigger than our sun. Our sun will not get to supernova. In fact, the next stage of our sun will be red giant, and then planetary nebula, white giant, and then black dwarf. It won't get to supernova. I will explain all that to you. So let's continue. Have I answered your question first of all? Confirm,
Yes,
please.
no.
Yeah, a supernova is a ball of.
It's an explosion, yeah.
No, I didn't say supernova. Okay, I was talking about nebula. Sorry, a supernova is an explosion. Yes, an explosion that takes place in stars. We thank God that we do not hear the sound on Earth. Why? Can you explain why?
Because they occur light years away, or
Yeah, light years away. But that's not just that.
or
Even if it occurs close to us,
supernovas have sound.
even if it occurs close to us, we still not be able to hear it. Because between the Earth.
Sound emitted from supernovas.
Pardon?
It's like when stars explode, the sound emitted.
So obviously, large sound, tremendously large sound.
Okay.
Tremendously large sound. But like I said, we can't hear it. Even if you're close to it.
Okay. Maybe the frequency is too high.
No, it's not because the frequency is too high. Yes, I know sound of very high frequency or ultrasounds are not audible to the human above 20,000 hertz or low frequency below 20 hertz. But it's not about the frequency. It's because between the earth and the stars or other planets or even the sun, you have space, vacuum. And sound does not travel through a vacuum. Sound does not travel through a vacuum. Do you know?
Oh, yeah, because space is a vacuum.
Space is a vacuum. Sound does not travel through a vacuum. Even if it happens very close to us, we only see it. In fact, a number of supernovas have occurred, and many of them are visible to the eyes. But we cannot hear the sound. We can only see the explosion and gas particles thrown into space. But like I said, not all stars will get to the point of a supernova. There's a particular mass of star that will go through that route. Some other stars will follow it. Okay, so a quick summary of that. Now, starting with the gas particles or dust particles, mostly hydrogen gas, the nebula, which is a ball of giant gas particles or interstellar cloud of hydrogen and dust, those particles will begin to be pulled together by gravity. Did you hear that?
Can you repeat?
Okay, I said I don't know if you can see the diagram, what I'm dotting.
I can.
Okay. Now these dust particles, mostly hydrogen gas and dust, will be pulled together by gravity.
By the force of gravity.
By the force of gravity, pulling them towards the center.
Then you now expand.
Let me explain. The force of gravity is this one I showed in red, pulling them together to the center. As they are forced or crushed together to the center, or compressed together to the center, it will get to a point where when there will be so much pressure and heat because of the pressing together of those gas particles. And the heat and pressure will be enough to start a nuclear reaction. Particularly nuclear fusion.
Yeah, nuclear fusion, yeah.
Nuclear fusion is what happens.
I heard of it during the reactivity class.
Yes. Nuclear fusion. And nuclear fusion is the joining together of small nuclei like hydrogen to form heavier nuclei, also releasing energy. So, I told you the gas particles in nebula are mostly hydrogen gas and dust. So the hydrogen gas, for instance, will be subjected to so much pressure and temperature that the nucleus of those hydrogen will begin to fuse together, join together, forming other elements. What is the atomic number of hydrogen? 1. So if you have one hydrogen nucleus, another hydrogen nucleus joining together, they can form a helium atom, and the energy is released. That's nuclear fusion. Just go to the previous page 13. Let me show you all that. Page 13, yes. You can see this hydrogen, this is deuterium.
I can't see your
my laser. My laser, but I'm on page 12. I'm at the top left corner.
Yeah, I'm on page 12 too, but I can't see the laser. Yeah, but I can't see
it will come on. It will come on. I think it's being delayed by the internet. Probably again. The equation, the nuclear equation, like that worked example is what I'm talking about. Can you see the nuclear equation where you have deuterium, hydrogen combining with another isotope of hydrogen to form helium? Did you see that? On the top left corner, top left. Can you confirm?
Yes, I can see it on top.
All right, so that's an example of a fusion reaction. It's usually hydrogen that undergoes that. So one isotope of hydrogen joins with another isotope of hydrogen, the nucleus, to make another element, and energy is also released. Energy, vast amount of energy is released. Now that energy that is released is what gives stars their energy, whether heat or other radiation energies. So go back to the page we are on, page 14 again. Let's continue. Page 14, please. Confirm if you are on page 14 now. Okay, so I was telling you about the gas particles being pressed together by gravitational force. So these red arrows show the gravitational pull on the forcing them to compress, gravitational force acting on them. And there will be a lot of pressure and temperature built up at the core of the nebula because of the particles being crushed together by gravitational force. You may wonder what that gravitational force is about, but every two objects exert a force on each other. Do you know?
Yeah.
Every two matter exert a force on each other. If you have a matter like matter 1 and you have another matter, matter 2, there's a force between them, a force of attraction, which we call gravitational force. You will do that at A levels. The value of that gravitational force is given by G and product of the two masses divided by the square of their distance apart. Let me see if you can see the formula I wrote below. Gm1 m2 over r squared, where r squared is the product of their distance apart. So you can see what I was talking about. The Gm1 over m1 m2 over r squared. Okay. Well, this is not something that should concern you now. You do it at A levels. I was trying to tell you that there's a force of attraction between any two objects. If you place a pen and a pencil on the table, there's a force of attraction between the pen and the pencil. There's also a force of attraction between you and your brother who is sitting next to you, or you and me who is even this very far from you. Pardon?
So can you repeat?
Okay, I said there's always a force of attraction between two objects. Every two objects exert a force of attraction on each other. That is what we actually call gravitational force. Gravitational force is not just weight. Weight is...
So is there gravitational force between any two objects?
Any two objects, between you and your pen that you're holding, between you and your book, between you and your laptop, between you and every other person in the house, even between you and me who is several kilometers away from you.
Is there a reason?
Is there what?
Is there a reason?
Is there a new thing?
Is there a reason?
Oh yes, that's the way it is. But these things are a little bit beyond your scope, so we won't get into the details. Gravitational force is a broad concept. If even what I'm talking about now, you will do it at A levels. The aspect I'm even looking at, there's a reason. There's a reason for that. There's a big reason for that. every two objects exert a force on each other. In fact, the earth exerts a force on you. You also exert a force on the earth. And that is what we call, as weight. That's why when you are trying to jump out of the earth pulls you back. But you're also pulling the earth to yourself. Except that since the earth is more massive, you are the one that comes back to the earth. There's also a force of gravity between the earth and the moon. And it is that force of gravity that keeps the moon in the orbit around the earth. Also, there's a force of gravity between the sun and the earth. And it is that force of gravity that keeps the earth moving around the sun.
That keeps the earth in orbit.
Around the sun. Or other planets around the sun. There's a force of gravity between the earth and any satellite, artificial satellite or natural satellite in space. And it is that force of gravity that keeps the satellite orbiting the earth. You know the name of that force of gravity if it is causing it to move in a circle. We call that centripetal force, isn't it?
Centripetal.
Alright, but generally there's a force of gravity between any two objects. The value of that force is the product of their masses. Like this illustration I'm giving you here. One has a mass of m1, the other one has a mass of m2. If you multiply their masses and multiply it by what we call gravitational constant, not gravitational field strength, gravitational constant, big letter G, and then you divide it by the square of their distance apart, you will get the value of that force. Real force that we apply extensively. In fact, you need to apply this thing extensively to be able to place satellites in space. I was telling you yesterday how satellites are placed at a particular position in space so that they cannot beat the earth and have an orbital period of 24 hours. Because if they don't have an orbital period of 24 hours, pardon? Were you talking?
Is it so that they can be the same place at the same?
Yes, they will be on the same point every time. Because if they are orbital period, that's the time it takes them to move around the earth once, is 24 hours. And since the earth is also spinning on its axis and making a complete spin every 24 hours, we will not notice any changes. It will look like they are at the same spot, even though they are moving. Just imagine this is the earth spinning. Did you see? I hope what I've even done has shown at your end, because from what you're saying, it takes a while for it to show. Okay, let me try and go to around where you are and see if it show. Assuming this is the earth, well, eventually when it shows, you will see okay, you've seen it. Spinning about its axis. Remind me again, how long does it take the earth to spin about its axis once?
24 hours.
24 hours. It takes 24 hours for the earth to spin, make a complete spin about its axis, 24 hours. And then you have a satellite in space, which is also moving around the earth and takes 24 hours to make a complete turn. It will look like it is on the same spot, because it takes 24 hours to move around. So we will always be seeing it at the same spot, and it is good for us so that whatever signal we send to it will always be received from the same position and sent back to the earth to the same position. Not at a certain point we are no longer seeing it, or it's no longer receiving the signal, or it's no longer sending the signal to the exact position on the earth. So it is spinning around the earth, making 24 hours of, it is rotating around the earth every 24 hours. So as the earth is also spinning about its axis every 24 hours, that satellite will appear to be on the same spot. We call that geostationary satellite. Okay, but the point I'm trying to make is the force that keeps this satellite in orbit around the earth is the centripetal force. You know that?
Yes.
Okay, and that is because of the gravitational pull of the earth on the satellite. the gravitational pull of the Earth on the satellite. And that's the satellite. Every two objects exert a force on each other. The one that will revolve around the other will be determined by their masses. The smaller one, the one with the smaller mass, will eventually move around the one with the bigger mass. There's a speed we can move you in space, and you will end up spinning, revolving around the Earth. Okay, let me not go there. You will be free falling around the Earth, but that will be a little bit difficult for you to appreciate. Now, so let's not get there and complicate issues. Now, back to the matter. Every object exerts a force on itself, and every object exerts a force on another object. So the particles, those nebular particles, exert a force on each other, which is concentrated to the center. That's what causes the crushing of those particles. So they are crushed towards the center to an extent that there's such a high temperature and pressure built up at the center. And that high temperature and pressure, extreme temperature and pressure, will be required to start a nuclear fusion, which is mostly joining of two hydrogen isotopes to form a helium, and energy is released. So now, good. When that starts happening, the energy released too will begin to exert a force in the opposite direction. These ones I showed in yellow. This ones I showed in yellow is representing, or the arrows are representing, the outward force as a result of, due to the nuclear energy. I will explain better. You know, whenever an object is heated, it expands, isn't it? Whenever you heat an object, it begins to expand. So that nuclear fusion is releasing a lot of energy, which will begin to make the center so hot, and the force will be pushing apart those particles again in the opposite direction. Once the force of gravity is balanced by that outward push, it forms what we call a stable star. The gravitational force equal the outward push. You have a stable star. It is stable. It's not crunching, neither is it exploding. Usually when one force is bigger than the other, if the gravitational force is bigger than the outward force, it will crush the particles much more. If the outward force is bigger than the gravitational force, they can be pushed apart up to a point of explosion, like you have in supernova.
In supernova.
Yes. What did I say is responsible for the outward force?
Thermal expansion.
Thermal expansion due to what?
Due to thermal expansion due to
the nuclear fusion.
Yes, nuclear fusion.
Outward force due to thermal energy. Let me write it like that. Thermal energy released during nuclear fusion. Or released by nuclear fusion. Read what I wrote in yellow if it has shown at your end.
Alpha field due to thermal energy is released by nuclear fusion.
Outward force due to thermal energy released by nuclear fusion. So when the two forces balance, it forms a stable star, what we call main sequence star. Right? Did you hear me?
Yes.
Our sun is a main sequence star. It is in a state of a main sequence star now. The next stage of our sun will be red giant. And from red giant, it will get to planetary nebula. What do you think will be responsible for the planetary nebula? The outward force would have become much bigger than the gravitational pull, is it not? Look at the diagram I'm showing, where I have the sequence down. I just want to summarize all that. Please, are you looking at the diagram?
Yeah.
From the state where our sun is now, which is main sequence star, the next stage is going to get to is the red giant star. From there, it gets into planetary nebula. You know, it has become bigger in size, more or less having expanded a little bit, because the outward force is bigger than.
So can planets form from those planetary nebulae?
Yes, planets can also form, particularly when certain particles that are sprung into space pull together. In fact, planets can also form from nebula if the crunching, are you listening to me? If the crunching of those particles did not produce nuclear fusion, what you just have is a planet or an asteroid or a comet and all those stuff.
Asteroid.
Yes, just a ball of rock or a ball of mass which forms a planet. But it doesn't have enough pressure or temperature to start a nuclear fusion at the center. And so there can be energy released to even set it ablaze. You know, stars are actually burning because of the nuclear fusion taking place that has engulfed the entire star. The nuclear fusion releases so much energy that it literally sets the star on fire, you know, so to speak.
Yeah.
That's what we see as heat and light and other radiations. But if the gravitational pull is just not sufficient, it can still press the particles together, forming planets or other celestial bodies like asteroids or even satellites of other planets like the moon. Do you understand?
Yes, sir.
So that's how those other ones are formed. The only time they will become a star is when the pressure is big enough to set up a nuclear fusion
Nuclear fusion to occur.
occur. Okay, so I was running through this. The main sequence star is where you have a stable equilibrium or an equilibrium of the two forces. Outward push of force due to the thermal energy released by nuclear fusion and the force due to gravitational crushing of the particles together. If they are balanced or at equilibrium, you have a main sequence star, and if some other things happen later on, it will move into, depending on the size of the star. If the size of the star is about the size of our own star, the next stage will be red giant, then to planetary nebula, to white dwarf, and then to a black dwarf. But if it is a star that is several times bigger than our own sun, something about 8 times or 9 times, it follows a different life cycle. It will also get to what we call red supergiant. Then to That supernova I talked about, when it begins to explode. And if it explodes, there's a particular way it can happen, and it will change into what we call a neutron star. A neutron star is a star.
Black hole.
Pardon?
So what makes it turn into a black hole?
Please speak up.
What makes them turn into black hole?
Okay, beautiful. I wouldn't want to dwell so much on that at the expense of the next thing we're going to do. It is in another lesson which I can refer you to. I will show you what it is in the next lesson. But let me just satisfy your curiosity with a very simple explanation. Go to the next page. Are you on the next page?
Yeah.
Okay, so I said, first of all, if it is a star, if it is a star about the size of our sun, it starts from the stellar nebula to a protostar, and then to a stable or main sequence star. From the main sequence star, it gets into red giant, then to planetary nebula when some particles might be flung into space again, and then from there you have a white dwarf. From whatever is left, do you understand what I'm saying? Just watch this, what I'm circling. Some parts have been flung into space, some other thing might be left. This inner core that is left forms a white dwarf. Did you hear me? Please confirm if you can hear me from there.
Yes, I can hear you.
And then that white dwarf will eventually form a black dwarf. That is the end of the star that follows this life cycle. An example is our own sun. Now, if it is bigger than our own sun, it also starts from the stellar nebula to a protostar, and then to a main sequence star where the forces are balanced, both gravitational force and the outward push due to the nuclear force. Then from the main sequence star, it gets into the red supergiant and the supernova. Now, two things can happen, because I want to satisfy your curiosity. Two things can happen. From the supernova, it can form what we call a neutron star, where the temperature is so high that all the particles are existing as neutrons. They've all changed to neutrons. No proton, no electron, only neutrons.
No electron.
Only neutrons. Right? Or it could follow another path where it becomes a black hole. Now your question is, what is the black hole? Now, first of all, read what I said about the neutron star on the bottom left.
And, is it still page 15?
This same page, the bottom left,
Okay.
you can see the neutron star. Okay, start from supernova. Start from supernova because it runs from supernova into it.
Supernova. Once the fusion reaction inside the red supergiant finally
Finish.
the core of the star will collapse, suddenly causing a giant explosion.
Yes,
This is called a supernova.
yes.
At the center of this explosion, a dense body called a neutron star will form.
Okay, just a moment. Just a moment, please. Once the fusion reaction inside the red supergiant finally finish, the core of the star will collapse suddenly, causing a giant gigantic explosion, which is called a supernova. At the center of this explosion, a dense body called a neutron star will form. Now I said the neutron star consists of just neutrons. The outer remnants of the star will be ejected into space. Remember I told you that our sun is even a product of a previous star. Are you listening?
Yes, sir.
The outer remnant of the star will be ejected into space during the supernova explosion, forming another planetary nebula that will start a new cycle. You know, it always starts from planetary nebula or stellar nebula that will start a new cycle of star, or that can start a new cycle of star. It says the nebula from a supernova may form new stars with orbiting planets. Did you read it? Read what I just circled.
Yes.
Read what I just circled.
The
Please try and stay alert. I need it to be more audible.
nebula from a supernova may form new stars with orbiting planets.
That is how our own sun was formed. In fact, I said our own sun is a product of a previous star, a previous big star that actually underwent a supernova. Now the remaining part, that will be the remaining central dense part, is what forms a neutron star, consisting of only neutrons. Okay, now this is what happens in a black hole. Are you listening now?
Yes, sir.
Good. That leftover, after some parts have been poured into space, whatever is remaining will be crushed together so much by a force of gravity that even light cannot escape from it. The force of gravity is so much that anything that comes across it will be pulled together to the center. So even light cannot escape, not to talk of any other object. And that is how the name black hole comes from. It doesn't even allow light to escape from it. And every other object that gets close to a black hole is trapped, because nothing can escape a black hole. So it just gulfs up whatever comes across it, including light. Okay, so a black hole is extremely dense point in space that not even light can escape from. And that's where it gets the name the black hole. That's the last stage of a star that is about 8 times the mass of our star, our own sun, which we call 8 solar mass. When we say 1 solar mass, it is the mass of our star, our own sun. If we say 5 solar mass, it's 5 times the mass of our sun. 8 solar mass is 8 times the mass of our own sun. It's usually good. All right. That's about the sequence of the life cycle of a star. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to 2 main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.